Hello, good afternoon, good morning, good evening, depending on where you're joining us from. We're at the European Space Agency today to spend the next hour with you talking about Mars, talking about asteroids, and talking about ESA's first planetary defense mission, Hera. My name is Josh. I'll be your moderator for the next hour. Thank you again for joining me. And we are at ESA's European Space Operations Center in Darmstadt in Germany. It's from here that ESA's teams fly spacecraft around Earth and out across the solar system to distant destinations such as Mercury, Jupiter, or perhaps even an asteroid. In any direction I look from our studio set here today, I can see a control room. There are people actively flying the spacecraft right next to us, walking past. So we're in a very live, active location. And I'm joined today by Hera Mission Manager, Ian Carnelli.
Hi, Josh. Thanks for having me.
Thank you for being here. You have had a very exciting few days, or perhaps a very exciting few years. Thank you for joining us today after a busy evening. I would like you to be the one to give us a brief overview of the Hera mission. So what does Hera hope to achieve? Where is it going? And how does it relate to NASA's DART mission? How are the two?
All right. So look, I'm super happy to be here today and share the excitement of this incredible mission. I think it's one of the best missions we are pulling together. It took us 20 years to get there, so you can imagine the excitement you will go through today, especially because last night, which was a very short night, I think we slept like 3 hours, we flew by Mars to gain energy, and this gave us more than 1,000 images. I don't want to spoil that, but that was absolutely breathtaking. And you will hear from the scientists later what they manage already to process. So it's really fresh information. And I'm super excited that everybody around the world can get to see these images just a few hours after receiving them. I think this is absolutely brilliant. So Hera is going to a special asteroid. It's a binary system called Deimos. It's a big asteroid of 800 meters with a small moon orbiting around it. And the whole purpose is to go back to where the NASA's DART mission impacted 2 years ago. So we sent a probe to deflect an asteroid, to change its orbit, right? And now we're going back to get all of the scientific data to turn this test on one specific asteroid to a technique we can apply to any other asteroid, and therefore to put in place a fully fledged insurance policy for planet Earth. Asteroid impacts are the only natural hazard we can detect, we can predict, and we can also avoid. And this is what we're doing today.
Thank you, Ian. That was a great overview. There was one particular asteroid in the news recently, asteroid 2024 YR4. You may have heard of it. It's been deemed entirely safe. Don't panic. But it once again raised that nagging question: if we ever did detect an asteroid on a collision course with Earth, could we do anything about it? What could we do about it? ESA is working on a number of planetary defense projects that address this topic, and Hera is one of our flagships.
Absolutely, and that's why we were also relaxed the other months. I mean, despite the fact it was a huge amount of work, now with DART and Hera, we can say we have the means to deflect, and if an asteroid comes, we know exactly what to do.
Yeah, it's very reassuring working with these people. Cool. I'd like to ask you, why Hera was at Mars then? So if Hera's on the way to an asteroid, it's an asteroid mission, it's protecting Earth from asteroids, what was it doing at Mars last night?
Well, I'm a bit embarrassed to talk about it here, which is the temple of flight dynamics and mission analysis. But in very simple terms, what we're trying to achieve is to use the minimum amount of energy to reach the target. The more propellant you put on board, the more energy, the bigger rocket, and the more it costs. So to save energy, there is this very smart way of flying by planets, and Mars was exactly at the right spot. And here I want to acknowledge also Michael Kahn and Pablo, who had done the trajectory for this mission. And it was exactly where it needed to be for us to get to Deimos and save propellant. So we literally used the gravity of Mars to pull us and then throw us deeper into space, and therefore harvesting a bit of the Mars or the planet energy. And then we did a very funny thing. A few weeks after launch, we corrected the trajectory so that while we were flying by Mars, we would get very special images. I will not spoil that.
Yeah, actually, I did want to ask you. You've seen the images, obviously, that we're about to reveal.
Yeah.
In order to build the anticipation just a little bit more, I wondered if you could tell us a little bit about the emotions that you were feeling as they came down from the spacecraft yesterday. There was a room full of scientists looking at a big screen, looking at their laptops.
Look, I was in the control room. I was privileged to be there for the acquisition of signals. So here I was pointing to Mars, and therefore we could not communicate with the spacecraft. And then we were in the control room waiting for the signal to be back and the images to come, right? And so that was, I was almost in tears. I mean, I know probably this is normal for a flight, for spacecraft operators, but every time we lose contact with the spacecraft, I'm super nervous. And then I was running to the room where the scientists were, and as soon as I opened the door, they were screaming. They were really screaming. I was like, what's going on, right? So I ran to the back of the room, and there was a big monitor showing the first picture, and I won't spoil it, but it was breathtaking, absolutely breathtaking.
After working so many years on this spacecraft, and then finally in October last year, seeing it take off and leave Earth for good, it must have felt like it was your child sending back a travel postcard, sending back these, look, I'm out here, I'm doing great. Here's where I'm. Here's my adventure. Here's what I'm exploring.
It's a huge achievement. I can't stop saying it, and I get very emotional. It was a huge amount of work from the industry team, from the scientists, from the engineers in ESOC, and everybody working together for 4 years among COVID and many other things that happened during the mission. And everybody worked, giving all the energy, the passion, and the dedication to have this mission. So having Hera performing so flawlessly, it's fantastic.
I think you've built up the anticipation perfectly. Right. Thank you so much, Ian.
Thank you for having me.
We will reveal the first image now, and we'll be joined by our next guests.
Thank you. See you later.
Thank you, Ian. Ta-da! There we go. That's the first of the images from Hera that was taken yesterday. I'm joined now in the studio by two more very special guests. Yeah.
Hey, Josh.
Hey, good. Hey, Josh. Hey, good afternoon. I'm joined by Patrick Michel, Hera Principal Investigator, planetary scientist, and I'm joined by Dr. Brian May, astrophysicist and stereoscopic imager.
Absolutely.
Thank you very much for joining us, both of you. We're really excited to have you here.
Absolutely, it's a pleasure.
Yeah, absolutely.
I've been talking too much already. I would really like to get you to explain what we can see here and why it's exciting.
Okay, so we are the scientists that screamed when Ian Carnelli came into the room, because effectively what we see here is Deimos, which is one of the moons of Mars. Mars has two moons. One is called Phobos, about 20 kilometers in size, and one other moon called Deimos, which is about 12 kilometers in size. So Deimos is the most distant moon of Mars. And the big question we have is, what is the origin of those moons? And so we have two scenarios. One is they are captured asteroids, because you can see it's very dark, and they look like what we call carbonaceous asteroids, the ones that are rich in carbon, very dark. But we have problem with this scenario because they evolve around Mars in a way that is difficult to make it captured. But we cannot rule it out. The second possibility is a giant impact. So like the moon of our Earth was formed by the giant impact on Earth, Mars also experienced giant impact. And it may be that maybe debris of the material that was ejected from Mars when there was a giant impact. So we try to understand that. And there are missions that are going to take samples of Phobos, like the MMX mission by JAXA. And you will have some Japanese colleagues later on that will bring back samples. For Deimos, we don't have as many images as Phobos. So all opportunities to see Deimos are high value. And I really appreciate the operation team, because initially, of course, the main objective of this flyby is to put Hera on the correct trajectory to reach Deimos in 2026. But, you know, when they start talking with scientists, they should never. We ask them, you know, Mars has two moons. Could we at least make a flyby that allow us to see Deimos? And they accepted. But that's a challenge. I have to change the trajectory to do so. And so eventually we were there yesterday waiting like with impatience to get these images. And this is the first image that we have from the asteroid framing camera, which is led by Jean-Baptiste Vincent from DLR. And this shows you Mars on the background and Deimos on the foreground. So this 12 kilometers, and you see the opposite side to Mars. So usually we have many Mars missions that took some pictures of Deimos, but usually it's on the side facing Mars. So here we have unique images from the opposite side. It's the first image. We are still working on it, so we have to see what we get scientifically. We hope we'll do some science, and thanks to Dr. Brian May, who makes stereoscopic images. So basically he's going to describe, allows you to see them in 3D. And you know, the vision in 3D, first of all, is a jaw-dropping, chair-falling, as I say. I always fall from my chair when I see that. But also it has high values because you see characteristics that you cannot see in 2D. So maybe, Brian, you want to say something about it?
Yes, absolutely, yes. It's early days, as Patrick said. We have a lot of processing to do, and some of these images we only actually saw for the first time this morning, a couple of hours ago. But already we have some nice stereos. It's very hard to communicate this in in mono, but I'm going to post these on my Instagram. So if you see that, and if you go to my Instagram site, you'll see also some instructions, and preferably look at the images through one of these stereoscopic viewers. What happens is you feel like you're there, and you see the whole scene in front of you in 3D. This particular image is nice in color. I don't know if you can see that. But as I say, I will be posting soon. Oh, now you see it on the screen. So if you have your stereoscopic viewers at hand, or if you can free view your screen, as a lot of people can, you can see that Deimos will pop out in relief against the background of this beautiful picture of Mars. What is actually more interesting is that we can zoom in on this. This is the thermal infrared image, but we also have visual images which give you a bit more information about the topography. Yeah. And this is something we don't know much about in the case of Deimos. So what is fascinating to me, and this is very new, we only put this together about 5 minutes ago, is we have the beginnings of a stereoscopic image of Deimos itself, and I can show you this here. I don't know.
So here we see Deimos itself in the framing camera.
Yeah.
And now you have it in 3D.
And now we have it in 3D, and shortly we will communicate this to you. But in this you see the whole thing in relief, and you can see topological features. You can see this amazing saddle which seems to exist on one side. Yeah. And we don't know much. You can just kind of imagine it there.
And in 3D, these are craters actually. You can then see that there are depressions.
Yeah, you can see some little craters down here. But the impression we get, and we can do some serious science from this.
Absolutely.
But also it's instinctive. You know, this is great outreach for us because people can see this and go, wow, I feel like I'm there and I can understand what this object is actually like if I could touch it.
And so the beauty is when you put them in the two images and then you put the glasses and it turns into a 3D and you see really Deimos very distant from Mars. Yeah. The round shape of Mars also is really beautiful.
Yeah, so this is something good, and it will be the next book, right, Patrick?
Absolutely, I'm happy to do so.
The next 3D book.
It's really amazing to see you doing that on live. Like yesterday, we were retrieving the data. We were asking the instrument lead, like Julia, who is online, Jean-Baptiste, give us the data because we want to do these stereos. And Brian was playing with initially poor data, and yet you were able to do things that are just crazy. So it's really exciting. So thank you for doing that.
There we go. We have an image. We have an image of the emotions as the images were.
You can see the emotion there.
So you see that our mouths are open, meaning we scream. Yeah, so this is when we received actually
when
the
we first see
image
this beautiful image
of Deimos and Mars behind.
That's a spoiler. That's coming up next.
And you know, for the public, maybe it doesn't mean anything, but for us, it's years of work. And the fact that we never saw Deimos that way, so having this successful immediately with a quick flyby was really a challenge. So
we have the GIF, the moving
and here
image.
we have the GIF image. So these are just images showing how Deimos goes over Mars. You can see. So we are facing, of course, the opposite side of Mars. You see here, and now we are working on the images. But and Brian is doing some stereo pairs where we see details on Deimos. So we learn a lot about its structure and probably how it was formed, although I don't think we'll answer the full question, but just for a flyby which was operational, we have a lot of fun.
This is all bonus, of course. The mission is about saving the planet. And it was only necessary to go past Mars to get this catapult effect, to get the right speed and direction to get to the eventual destination. But the science that we get from this is colossal.
Absolutely.
And I think we're all like children, you know, we still get so excited just to see this stuff. And I thank Patrick and also Ian, of course, for the opportunity to be here and participate in this.
And reminding me that I'm 4 years old, actually, in my head.
Yeah, right.
And a final interesting thing is that we are going to see Didymos and Dimorphos, which is, Dimorphos is a moon of an asteroid, and we flew by a planet that also has its small moon.
Yeah.
So, you know, it's interesting, this analogy. Of course, the size difference between Dimorphos and Didymos is not the same. This is very small. This is 12 kilometers on a very big planet. Dimorphos is 150 meters around an 800-meter body. So, but there may be some analogies because we believe that Dimorphos was formed by mass shedding from Didymos. So Didymos is rotating, losing mass, and formed Dimorphos. And maybe that's what happened with Deimos, if it was a giant impact.
You were saying this is a rubble pile?
Maybe.
You're saying this?
Maybe. Who knows? I hope with your stereo pairs we can say something
Well,
about
I hope
it.
nobody's going to hit it in the near future, because then we find out, right? Please no.
Sorry.
I was going to say no projectiles on this, please.
No. On the other hand, Phobos is falling on Mars. So the other moon is falling on Mars. In 40 million years, it will fall on Mars, and Deimos is going away. So you have two moons, one falling on Mars and the other one going away. So this one is safe.
Yeah, in the case of Dimorphos, we really don't know what we will see.
Absolutely.
Because it's already been impacted by the DART mission. And we didn't get a very good look at it before that happened, but we get a very good look at it afterwards.
Absolutely, and in fact, it's true. If we go back to Deimos in a few years, it will be the same. While Dimorphos, from the DART impact to now, we don't know. We have images before, and we're going to discover what it is after, so which is very important and very exciting.
Maybe you could explain briefly. This looks much more like the red planet than the first images we showed. This is false color, correct? We added this red tone. So maybe you could explain.
Yeah, it's how it would look, because of course the asteroid framing camera doesn't have the colors when you observe. So we try to convert in how it would look like with our eyes in visible wavelengths.
So a bit like what Brian's doing with the stereoscopic imaging. We're trying to how you would actually be able to see it.
Exactly, and you can see it's as I said, it's very, very dark. So, and I hope that with Julia's instrument, we'll be able to say something about what we call the spectra, which gives you hints about the composition, because the origin of the moon is related to its composition. If it has a composition of a carbonaceous asteroids, it points to the captured object. If it has a composition which says there may be some basalt or thing like that, maybe it could be a part of Mars ejecta. So that's very interesting. But yeah, it's a very, very dark object over a red planet, which makes it even more beautiful, I think.
Thank you both very much. Sorry that it's a lightning schedule. We've got so many great guests, but thank you so much for that.
Thank you, Josh.
I hope you'll both be able to.
Thank you so much, Brian, because what you do is really beautiful and scientifically very important for us.
Thank you. Thank you for the opportunity.
Thank you, Brian. I hope you'll both be able to stick around a little bit in case we get some questions from the audience later. Yeah, cool. Thank you very much. Thank you very much, Patrick and Brian. That was our first set of images from Mars from yesterday that Hera took. I would now like to introduce the next image, which is from, there we go, which is my new laptop screensaver. This was taken by Hera's HyperScout image and instrument. And we have Julia de Leon joining us remotely to explain what we can see in this image and why this one is exciting. So, over to you, Julia.
Hi, Jess. So thanks for giving me the opportunity to join this event. I'm super happy. I'm super excited. And as Patrick was mentioning, we were all just willing to see that, first of all, the instrument was performing well, which we already knew from the Earth-Moon system images that we took shortly after the launch. But, this is like kind of a bigger image and a bigger object, and we were just wanted to check that everything was perfect as it has been. I mean, it's amazing to me. It's even I'm participating in the mission, and to me, it's even like a miracle that the flight dynamics guys can make this happen with so accuracy, and the images were just coming as we were expecting, which is amazing. I mean, exactly the same way, same position. It's amazing. And okay, I can explain a little bit. This is basically Mars on the background and Deimos in front. And this has been obtained with the HyperScout H instrument, which provides color information. This means we can retrieve some more info on the potential materials that might be on the surface of Deimos, which, as Patrick was explaining, they're just one mission that has been able to obtain images on that side of this moon, because all the images have been taken from the face that is, the side that is facing Mars. And it's been only the HOPE probe that on 2023 was taking the first images of that side. But the good news is that their instruments were not covering the wavelength range that we are covering with HyperScout H. So this actually would be the very, very first images of this phase of Deimos obtained at this wavelength, this spectral region.
So this is literally Deimos like we've never seen before.
Yeah, exactly. I can say that.
Cool, thank you. Yes, you mentioned that HyperScout H, it collects color information. Maybe you can explain a little bit. So Hera's destination is a binary asteroid system. So two asteroids. Mm-hmm. They are presumably quite grayscale, black, gray, maybe some lighter patches, maybe some darker. How does color play into that? Or what do you mean when you say color? And what can the color tell us?
Well, it's basically what we see with our detectors in our mobiles, that we have an RGB. We have different filters that take the light, some part of the light that we see with our eyes. The HyperScout H instrument is more or less the same, but instead of having 3 filters, we have 25 filters, which goes a little bit beyond what the human eye can observe. So we go a little bit to longer wavelengths in the spectrum. And at those wavelengths, what we basically see is, okay, so the sun is illuminating the materials on the surface of the asteroid, and we see reflected light. And what we can see is how these materials are absorbing this light, and these absorptions appear in this color information that we will get, and will tell us the type of minerals that we have on the surface of the asteroid or the planet or whatever surface we are looking at.
Yes, and so we should touch upon the fact that it's important. You can build an instrument on Earth and you can be as confident as possible that it works, but nothing really works until you've tested it in space.
Yes.
And would you like to maybe comment on how unique an opportunity this flyby was to test Hera's instruments, especially HyperScout H?
Yes, it is important because the filter pattern on the detector makes this instrument a little bit particular. So we can also use star observations to calibrate and to check how the instrument is performing. But with this instrument, we need extended objects. So we need something that covers the full detector with information. And we have Mars, we have the surface of Mars for that, which is perfect because we know the composition of the surface of Mars. It's been, observed extensively. And we can use that to check how our filters, our detector is working, and to confirm that it's working properly. And if even needs some adjustment or some calibration factors, we can compute them. So these observations, only Mars observations, are very, very important for us for calibration purposes. But we have this Deimos Plus, which is an extra, and we can also use it as a test for our upcoming observations on a surface like Deimos is an asteroidal surface.
Yeah, whether or not, as Patrick was explaining earlier, Deimos' origin is not entirely understood, but nevertheless, it's going to be the most similar object to an asteroid that Hera encounters on its way. So it's a great opportunity to test the instruments on something asteroid-like, if not entirely an asteroid.
Yeah, that's correct. It's not only a test. We can, I think, my expectation is that we can really make some contribution to the science, to our knowledge on Deimos, on this moon. Because as I was commenting, we are providing data in just the gap where there are no observations before these observations. And especially some of the minerals that we observe on the surface of Mars have these distinctive signatures at the wavelength range that we are covering with the HyperScout age. So I have good expectations also on the science contribution that we can do with these observations.
That's true for you, and for the other instrument teams, the work has just begun. we
Yes,
raced
that's
you
correct.
all, we chased you all to get some lovely images for public outreach, but now you're really digging into the wealth of data that's behind these images. So you will be busy
Yes.
for the next 18 months before Hera then gets to its
You
destination.
bet, yeah.
Thank you very much, Julia. Thank you very much.
Thank you.
I'd like to take this opportunity to see if we have any audience questions for our first panel. So if you have questions for Dr. Brian May or Patrick or Julia or Ian, let me know. I have, should be able to see them here. Okay. We have one great question. I think this one could be for Patrick if he's around. Yeah. No, so we have a question. We have a question about the shape of Deimos. Why is it not spherical? Why is it so lumpy?
So that's interesting. So there may be different possibilities. In the giant impact scenario, basically you have a projectile impacting on Mars, and then you have debris that are ejected that make a disk. And in this disk, Deimos is formed by reaccumulation of pieces. And this scenario is correct. Of course, the way reaccumulation works can lead to many kinds of shapes. And it is small enough that it doesn't become spherical like a planet, just because it is small and the gravity is not enough to compensate the strength that is due to the boulders that are interacting together to form it. So that's why it's not spherical. And that's why asteroids are not spherical. It's also because you need to have a minimum size or mass to not be able to compensate any internal strength and therefore take a spherical shape. So that's why we think Deimos is not spherical.
Thank you very much. Let me see if I've got a question that you
okay.
would be the best for. Actually, I'll take the next one for Julia. Thank you.
Okay,
Thank you,
thank you.
Patrick. Thank you. Julia, somebody asks why Mars appears blue in the background of the HyperScout H image. We were talking about color, but we perhaps omitted the fact that the red planet doesn't look very red in this one.
Yeah, I was expecting that one actually. This is basically because, as I was mentioning, neither the surface of Deimos nor Mars are emitting light, so they are just reflecting the light of the sun. And we have not been corrected from that. So we are basically looking mainly at the sun's contribution, which is at the wavelength range that it operates our instrument. The sun will look bluer than Mars because Mars is red. So as we have not removed that contribution, that's what we are observing this in blue. I hope that the audience might understand this.
Okay, this is sunlight then.
Reflected sunlight, yes.
Yeah, okay.
So
okay.
we have to remove the contribution of the sun to get really proper colors from Mars. We have not yet done that. And that's why it looks blue, because Mars is redder than the sun, okay? And the visible wavelengths, so at least the wavelengths where we are operating with the instrument. And that's why we see it as a blue.
No,
so I hope the audience will learn something with this.
Yeah, definitely. Thank you very much. So we have lots of audience questions about our other special guests on the desk in front of me. Hera is part of, Hera is ESA's first planetary defense mission. It's part of our contribution to the global efforts to protect Earth against an incoming asteroid. Our ancestors were not so lucky, or our predecessors rather were not so lucky, and so dinosaurs have become a bit of an ambassador for the Hera mission. We like to say that dinosaurs they couldn't have done anything about the asteroid that struck Earth 66 million years ago. Don't quote me on that. I'm not the scientist. They couldn't have done anything. They didn't have a space agency. You living now in 2025, you're lucky. You have more than one space agency. You have multiple space agencies, and by combining our expertise and our resources, we think we have a better shot at protecting Earth now. But they're with us in spirit. With us in spirit. Okay. We have a question from the audience for Brian, if Brian is around. Sorry, quick one, I hope.
Yes.
It's about how the stereoscopic images are generated. What's the difference between the two images? Are they two separate images taken at different times or from different angles? So yeah.
Yes, the two images look very similar in every case. So you think, why do you have two images the same? But they're not the same. They are taken basically from the position of one of each of your eyes. So if I'm taking a stereoscopic picture of you, I will take a picture from here, and a picture from here. This picture will come to my eye in the stereoscope, this eye, and the other picture will come to my left eye. Now, in the case of Astro, of course, your eyes are much too close together to perceive the view in 3D. So what you do is you adjust your baseline. So basically, you have a baseline which can be thousands of miles long, and your one eye is over here and the other eye is over here. But the principle is the same. Yeah. You then feed these two images to your two eyes using a stereoscope. And the same thing happens as in real life. Your brain is able to put these two slightly different images together and get all the depth information it needs to see the thing in relief.
So these images were taken...
These are a few seconds apart.
A few seconds apart, yeah.
I think 10 seconds apart.
Yeah.
And these are thermal infrared images. And so you notice that Deimos comes out as much hotter than Mars behind, which is the case because Mars has a cold atmosphere and Deimos is out on its own. It's a black object, so it heats up quite readily. So we're looking at quite a relatively hot object here. But in stereo, you can actually see they're slightly different. If you look, from this eye, Deimos seems a little bit closer into Mars. This one's a bit further away. And this is what we call parallax. The parallax differences are something that your brain loves. And we do this every second of our lives. Every instant of our lives, our brain is putting together these two slightly different images and constructing a stereoscopic 3D image of the world around us. It's colossal. And without it, I mean, if you're unfortunate enough not to have the two eyes, everything looks very flat. If you try this right now, it's amazing how much extra information we're getting from the two eyes. This is not an accident. This is an evolutionary advantage to be able to see what might be eating you or what you might need to eat. Where it is. Yeah.
No, thank you very much. Perfect. Thank you very much for answering that audience question, Brian. Thank you. Thank you very much for your questions. Keep them coming. We should have hopefully some time to answer some more questions towards the end of the broadcast. We're now joined online by two more very special guests. We're joined by science fiction author Andy Weir, author of The Martian, Artemis Project Hail Mary, which I'm sure many of you are very familiar with and needs no introduction. And we're joined by ESA astronaut Alexander Gerst, who is also a geophysicist by training and is thus very enthusiastic about asteroids and their mineral composition and things like that. So welcome, Andy. Welcome, Alex. Thank you for joining us. If you can give us a hello just to make sure
Oh, yeah, a pleasure to be here. Thanks for having me.
Yeah, cool. Thank you very much. Andy, I'd like to go to you first. Thank you. First of all, thank you for joining us so early in the morning for you, local time. We really appreciate that. How did these images make you feel? How do real images of Mars make you feel as a science fiction author?
Oh, I just love looking at real images of Mars and seeing the real science happen. I get a real kick out of it. And I'm glad Deimos is getting some attention. It's always overshadowed by Phobos in general. But yeah, it's really neat. To the real scientists here, I guess this shows you kind of my ignorance. So Deimos is tidally locked, I guess. That's why we usually don't see the site of it.
That's a good question. That's my understanding. I'll throw the question into the room. Scientists, Deimos is tidally locked?
Yes.
Yeah, correct.
Okay. Yeah. Yeah, so it makes sense. It's kind of funny that, even though this is the side of Deimos that is usually pointed at Earth. The side that we have seen the most of is the side that's pointed toward Mars, right? Because that's where that's where we usually have our cameras in that neighborhood.
Exactly.
So that's
exactly.
pretty cool
Yeah.
too. I like that.
Yeah.
Yeah, as I mentioned, the timing on this ended up being about 6:30 in the morning my time, and my wife is on a business trip, and our nanny doesn't get here yet. My son doesn't usually wake up until about an hour from now, but today he decided to wake up early, so he's joining us.
We're thrilled to be joined. Extra special guest. We got more than we asked for. Wow.
Yes.
Thank you so much.
Your panel of and I guess I wanted to say for Alexander, I don't know if it's Dr. Gerst or Mr. Gerst or
it's Alex.
Yeah, Alex, that works. So you must be getting a kick out of all this additional info as a geologist, as an astrogeologist. Do you have an opinion on Deimos's formation?
Well, yeah. First of all, as an astronaut, also I appreciate the precision of orbital trajectories. Otherwise, I wouldn't be here right now. And so I'd like to congratulate the entire team for pulling this one off. I mean, we've talked about Mars and Deimos today, but actually, I mean, as we know, this is just a part of the journey for this fantastic spacecraft. And if you imagine Mars being, anything a few hundred million of kilometers out there, and we shoot our little probe there by it to collect energy. And we have to do that with such a precision that we don't slam into this planet, nor into Deimos, who looks awfully close there. So if you take this into account, I have to say kudos to the team for pulling this one off. And then, as you mentioned, Andy, yes, I'm a geophysicist and a geologist, so it's pretty cool to see Mars from close and those moons. I have to say I'm quite inspired by this. Of course, it's Mars is one of our closest neighbors. It's my second favorite planet, and it always fascinated me when I was a kid. I was standing out there, looking out at the night sky and seeing this orange dot up there, and wondered, hey, is there maybe life out there? Is there, how does it look like there? And I'm pretty sure you had the same, Andy. I read your novels.
Sure.
As you know, every astronaut feels a little bit uncomfortable reading your books because you're putting us into a work situation there. And I was thinking, oh my God, if I'm in that situation, how would I get out? Would I have the skills of a Mark Watney to save my life? And so I always felt quite uncomfortable reading your books, but then I love them anyways. So yeah, Mars is a place where if we as humans go there at some stage and look for life, and we are in the process of doing that, we have, for example, the ExoMars project underway. If we find traces of life on Mars, like maybe extinct life, maybe anything completely weird, but if we do find life, that probably means that the universe could be full with life. So this is something that is an amazement for me. I mean, that in my lifetime and in your guys' lifetime, everyone out there, we could potentially find an answer to that question that every one of us had when we were kids looking into the night sky, and even now, are we alone out there?
Cool. Thank you very much. Thank you very much indeed. Yeah, I agree with you entirely. Alex, you have some hands-on experience with asteroids. You did an expedition to Antarctica on the hunt for meteorites. Is that correct? Would you tell us a little bit about that? Obviously, they are the remnants of asteroids that have made it through the atmosphere and made it to the surface of Earth. What was that like?
Yeah, indeed. I was part of an Antarctic expedition, or one of my Antarctic expeditions. Actually, my fifth one was with NASA and as an ESOC participant to search for meteorites, which in Antarctica we can find them pretty well. They fall down everywhere on Earth, but in Antarctica we can find them much better because they they stick out much more in the ice. So we go there. We found several hundred of them, and it's one part of actually investigating what asteroids are made of. When asteroids fall down on Earth, then they turn into meteorites. And in order to learn more about asteroids, we need to look at them, need to find out what they're made of, what the different compositions are, so we can learn as much as we can about it to work on missions like Hera or DART, or to deflect an asteroid at a later point. We have to know a lot about it, otherwise, we don't know what happens when we hit it. And also, to understand a bit more about it, what happens if they hit Earth, right? What happens if we have an impact? As you might know, we do it right here in Germany. We have a 24-kilometer wide meteorite crater. Just think of that number: 24 kilometers wide. The whole city of Munich could fit in that crater. And that only dropped down here 15 million years ago. That's basically nothing in geological time scales. If you imagine that Earth is more than 4,000 billion years old, and only 15 million years ago this slammed down here. So that tells us this will happen again. And are we ready for that? I would say definitely not. So we need to learn as much as we can, and so that was part of that expedition I was on.
We brought up a picture. Oh, sorry, it's around bad timing. We brought up a picture of the crater in Germany that you were speaking about. Hopefully, you can see it too on your screen. Am I correct in thinking that these dark pieces of forest, they trace the crater rim?
Yeah, and that actually shows you part of the problem that we're faced with, trying to find out more about meteorite craters, impact craters, is that on Earth, even if they're relatively young, they're overgrown by vegetation. Like here, you can see a little bit of the forest that they let on the crater rim. But then there's a city of Nördlingen right inside. And so we have to look at very specific forensic traces of that meteorite inside. We were training in quarries that actually the Apollo astronauts also had trained in before they flew to the moon, because impact craters are everywhere on the moon. So we need to know how to describe them, how to recognize them. And the problem is that in order to find out more about the risk of a big asteroid hitting Earth, we need to know more about them, the distribution of sizes and ages, and that is really hard to get to know on Earth. And that's why we are actually planning to fly to the moon as part of the Artemis program, where we astronauts land, and one of our tasks will be to look at impact craters and try to date them and see how old they are, how many of which size they are, and to open up a statistical knowledge on how often it happens actually that an asteroid of a certain size hits the moon and therefore also hitting Earth with sort of a similar likelihood. That's one of the reasons why we, meaning one of my colleagues or I, have to fly to the moon.
Thank you, Alex. Andy, I'd like to ask you whether you've ever felt about writing something about asteroids, perhaps. While we've got Alex here, we could talk about potentially a crewed mission in which a human lands on an asteroid, or maybe an asteroid impact scenario, or a disaster avoidance scenario. Is that something that you've ever considered? Or am I spoiling your next book?
Not my next book. I do. But yeah, absolutely. I've considered that, and I even come up with a story that involves an asteroid impact. And the first thing I had to do was explain why there would be an asteroid impact that catches us off guard, right? Within this, fictional scenario of I can't just say an asteroid hits Earth because of all the planetary protection or planetary defense. Sorry. Those two terms are very similar and mean very different things. Because of all the planetary defense, I have to come up with a scientifically plausible reason why there would be a major asteroid impact on Earth that nobody saw coming.
Yes, yes.
So you guys working hard makes me work hard to like circumvent you in my fiction.
Well, actually, thanks for Andy. Thanks for the compliment there. It sounds like we have it all figured out yet. But to be honest, right? I mean, there's been flybys of significant size asteroids that zipped past between Earth and the Moon, and we found them in hindsight, right?
Mm-hmm.
And so I think there's still a lot of things to do for us, and that means there's still a lot of possibilities for you to find a realistic reason why we are not covered yet. And so I'm looking forward to reading that book, even though, again, I can see, I can already feel the goosebumps in my back. I can't say my hair raising here, because, you know, it would put us in a very uncomfortable situation.
Mm-hmm. Yeah.
Cool. Thank you, Andy. How you mentioned like when you get an idea for a book like that, then a potential idea. How do you do your research? How do you do your research for science fiction like that? Do you have contacts at ESA, at NASA, like, or do you like how do you approach that?
Well, yeah, people think I have like a contacts list just like full of scientists and like engineers and astronauts, and well, I kind of do, but I found that Google is pretty much all I need most of the time. It's kind of cool. Well, first off, I really love doing the research and math. It's my favorite part. It's the pesky writing that I don't enjoy. But the people who, you know, all the scientific information you need out there, it's cool because it's the people who make it are, first off, they're very enthusiastic, like all of you, just people who work in space and research about space. Yes, I know. Are very excited about it, so they're very happy to talk about it. Don't talk, huh? That's bad news, because there's these people want me to talk. Yeah, they do. I mean, they kind of want me to talk. I mean, they're not as bored of me as you are. Okay, there you go. Yeah, I'm not able to see the screen right now because I have a video of a helicopter flying around for him to look at on the screen.
We can hear you. We can see you loud and clear.
But you want to talk to them? No,
Thank you, Andy. No worries at all. We'll come
I'm
back
sorry. It's
the
perils of this time of the morning and my wife being on a business trip. It's
no worries at all. Thank you so much for sticking with us. That was really helpful. Thank you. I've been getting some more audience questions. We have. We have a question for Alex, whether you could imagine walking around on the surface of an asteroid. What would that feel like? Would you have to be careful not to walk too fast or to jump? Or like, you have plenty of experience in low gravity environments, so maybe that would be a very transferable skill.
Yeah, a short answer, absolutely yes. I can imagine myself walking around anywhere in space. So, as you know, we talked a little bit about the Moon. This is one of the next big destinations that it's important to go to. But an asteroid has been in the focus in the past several times. There's been quite a time when NASA was looking at sending astronauts to an asteroid. So we have actually, of course, thought about how it would be, developed some concepts on how it would be possible to go there, to capture one potentially, to see if we could potentially deflect it or make use of it in any other way. Space is also about using in situ resources, like when we were on the Moon, we want to use the water that we find there to generate oxygen to breathe, water, fuel, to travel further on to Mars. And so the same, is conceivable with an asteroid that we make use of it. So, walking on an asteroid is going to be quite complex because depending on its size, it might not have much gravity. So if it's only a few hundred meters, you probably wouldn't feel it at all, really. If it's more in the range of tens to hundreds of kilometers, you could feel a little bit of a small gravity. But would that be enough to walk on it? Probably not. So you would have to, it's this awkward thing in between, floating, being attracted there, and then, but still being weightless. So you bounce yourself off with the smallest motion and drift away. So you're half in an orbit around it, half already touching it. It's a little bit like the two CubeSats you're going to send out to Dimorphos, Milani, and Juventus that are in the same difficult situation in between. So it's actually quite challenging. I would say going to an asteroid, certainly not going to be walking on it, but going close, touching it, working with it is probably more difficult than going to the moon in terms of human interaction. Of course, there's other things that are easier. Like if you have a spacecraft to get close to an asteroid, it's probably much easier than to get close to the moon, as we saw with several of the moon probes that several companies sent to the moon recently. Some of them fell over, some of them crashed. It's tough to get there. It's probably going to be a little bit easier to get close to an asteroid, but then once you're there, very different than.
Cool. Thank you very much, Alex. Thank you, Andy. Thank you, Alex. If you're happy to stick around and we have more time for questions at the end, we'll throw them your way. But now it's time to reveal another image of Mars from Hera.
I'm going to have to get going, guys. Thank you so much.
No problem. Thank you so much for joining.
Apologies. The boy's getting a little fussy.
Thank you so much.
Good luck.
Good to see you again.
Bye-bye.
Thank you so much. All right. Bye-bye.
I'd like to welcome onto the stage Seiji Suguta.
Thank you, Josh.
Thank you so much for being here, Seiji.
Thanks for having me.
You're a planetary scientist at the University of Tokyo.
That's correct.
And these images were taken by Hera's thermal infrared imager,
Right.
which is an instrument provided by JAXA,
Yeah.
the Japanese Aerospace Exploration Agency.
Right.
Would you like to explain what TIRI does and what we can see in this image?
Okay, great. Well, this TIRI is sort of a thank you. Temperature imager. It maps out how hot the surface is, how cold the surface is. That's the basic function of TIRI. And then the purpose of this temperature measurement is to find out what kind of material, like what kind of compaction state it is. Like, is this really fluffy material of a fine grain stuff, really fluffily deposited on the surface, or dense, coarse material putting together? So that's the two extreme cases. And the distinguishing between those different cases gonna really help us understand the chemical compound and the spectral properties of Deimos and then also Didymos toward the end. So that's the basic idea.
We have another image available where you've colored. So this is obviously not the TIRI doesn't see color as such; it sees temperature.
Right.
So we've mapped or you have, not me.
no,
You've the team has mapped colors to temperatures. So we see hotter regions appearing yellow and colder regions appearing purple here.
Right.
Is this what we expected to see?
Yes. This really shows that our instrument is working really well. The color of a Deimos in the middle is brighter than the background Mars. Mars is showing up colder because of the atmosphere is slowing down the heat up of the surface. This is a high noon of both Mars and the Didymos. Deimos, I'm sorry. I got confused with the names of small bodies. But because the surface of Deimos is not protected by the atmosphere, it gets really hot. That's how we were predicting, and that's exactly how we are seeing in the resulting data. So that's really good.
Super. And this would be kind of a polar region on Mars then that's starting to get cold? Is that why Mars is hotter up here?
Well,
that's kind of the equator,
right.
and this is down towards the poles. Yeah,
That's
so
correct.
Also what you were expecting.
Right.
Yeah, cool.
And then this data, this is just like a raw data we just obtained yesterday, is showing qualitatively really good quality data. But when we analyze the data in this coming days and weeks, we will probably be able to tell the difference between this grain size and that grain size. That's going to probably tell us about something about the origin of Deimos. Yeah, not today or tomorrow, few weeks.
You can't make that declaration here live. No, we look forward to that. That's super. I'd like to ask you, so Japan plays such a big role in ESA's Hera mission. Is planetary defense and asteroids, are they a topic of widespread public awareness and interest in Japan?
Right. I think the awareness and the interest in the planetary defense and the awareness of the possible threat by the asteroid impact is growing in Japan. And then JAXA and the planetary science community in Japan are really eager to participate in this global international effort. And then Hera is one of the first effort we like to really contribute. And then possible Ramses mission, we may talk about later in the session, but that's the sort of direction of Japan.
Super, we can jump into that right now actually. We've got an image here of Apophis, the asteroid Apophis. Right. So the Hera mission is just beginning, but we're already looking ahead. And we've spotted another opportunity and another asteroid of interest, which is the asteroid Apophis, which will fly very close but safely past Earth in 2029. And ESA has proposed a mission called Ramses, the Rapid Apophis Mission for Space Safety, that would rendezvous and visit Apophis as it passed by. Patrick, I'd like to welcome you back on stage to talk about Apophis and about Ramses.
Yes.
If you could start by explaining...
Hello, Seiji.
If you could start by explaining what makes the Apophis flyby of Earth such a unique opportunity for science and planetary defense.
Yeah, this is absolutely amazing because Apophis, so this time is 340 meters in size, about twice the size of a football stadium probably, right? And it's going to come at a distance which is about 30,000 kilometers from Earth.
We have a little graphic
exactly.
here.
And the crazy thing is that this is the first time that we will be able to see with naked eye the light of an asteroid. So can you imagine you look in the sky in Europe, so Darmstadt if there are no clouds, otherwise you come to Nice, there are never clouds. Africa, part of Asia, you look in the sky, in the evening sky, and you see the light of an asteroid. And this occurs only every once in a 7,000 years, basically. So it's our unique opportunity because we don't live 7,000 years. And the great thing is that so far, all the missions we did to asteroids, including Hayabusa 2 by JAXA, showed that when we interact with an asteroid, the behavior, the response of the surface is not the one we predict. And despite the fact that we have images, we can think a surface looks solid, and when you touch, you just go through it, which is very counterintuitive. This is because they are very small, they have a low gravity, so everything is sensitive, and therefore we are still trying to understand how they respond to external action. In the case of Apophis, the great thing that nature does a job for us, because so far all the interactions were done by ourselves through sampling the surface, making an impact. This time we just need to observe the tidal forces of the Earth when Apophis come by and then goes away, will potentially perturb the properties. Maybe make surface motion, change of the rotation axis. So without touching, we just need to observe. And this is fantastic because we can do a lot of science, but also during the flyby, we can take images and feed them in live to the public that sees the light in the sky. So, people who were born when the astronaut went on the moon, they could see on TV the astronaut on the moon, and in their garden, the moon itself. And that remained the collective memory.
Yeah.
So we have this unique occasion to have ESA offering images to the public. I mean, I can imagine a child looking at and then on the screen, the real image of the astronaut. It's going to be totally crazy. Yes.
Yeah, no, I just wanted to say, Ramses would also then feature strong Japanese collaboration.
Right.
Seiji, is this something that Japan is excited for too?
Really excited about it. Yeah. And the Ramses is going to be a good copy of a Hera. Hera is really ready to fly, and then it's going to be a short track, and then we have been already in a team, and then the instruments in it, and then the upcoming planetary defense has to be done in an international framework, and then we're really happy to be really contribute to it, really rapid response, and then good collaboration. That's what we are really excited about.
And in fact, time is short because we need to launch in 2028. We are in 2025. Time is short also for the live, so I have to be quick. But, is approved to be able to develop in a short time scale a mission. Hera was only developed in 4 years, and this is a complex mission. You have a spacecraft and 2 CubeSats. The first time you do deep space exploration of an asteroid with 3 components. So in order to save time and do it in three years, we basically rely on all this expertise gained with Hera, using essentially the same platform adapted to Apophis, with also CubeSats, maybe for the first time seismology, because we may land a CubeSat on Apophis and see how the seismic waves are going through the surface that tell us something about the internal structure. And with our Japanese colleagues that will work so well, they are so kind and so powerful.
Hopefully.
So we will again demonstrate, and this will be an important message. Can you imagine in 2029, the world watching Apophis, and we have different countries working together, followed by NASA a few weeks later with their mission, and showing to the world that despite all the geopolitical tensions, when it's about protecting the planet or doing science, we erase the frontier. And I think this is the best message we can give to the world.
That's a fantastic message to end this section on. Thank you so much to both of you for joining me. Thank you so much. That was really good. Thank you. We are a bit behind time. I'm just going to do a quick double check if it's okay if we run for 10 more minutes. Nobody's shouting at me not to, so we're going to run for 10 more minutes. I'd like to welcome back on stage Ian Carnelli, Hera Mission Manager. And you may think that the star-studded lineup that we've brought to you so far is already quite impressive. We have one more special guest. Ian has brought with him a very special friend of his. Ian, if you would like to introduce who you've brought with you.
Yeah. So I brought a friend, and we're trying an experiment. Like this mission has a lot of experiments. We're bringing the first time CubeSats into space. We're doing autonomous navigation, visual-based navigation on board. Fantastic technologies you will see in the future. But I have one more surprise. I brought a friend with me today. Let's see. Hello, Hera. How are you doing? Oh, volume. Let's see.
It's the nature of experiment.
We're experimenting here. This is the first time in the world we're doing this. Hello, Hera. Can you hear me?
Loud and clear.
So how are you doing?
I'm doing fantastic. Zooming past Mars was a thrilling experience. The view was simply out of this world, and I even got to see Mars's moon Deimos up close. What's on your mind today?
Well, I'm here with Josh from the ESOC Communication, and we're live streaming you to the whole world and presenting you to everybody and telling the public that you can actually provide science and telemetry. So can you tell me what your systems are like right now?
Great to hear you're live streaming. My systems are running smoothly, featuring a sophisticated design with 14 square meters of solar panels powering my journey. I have omnidirectional low-gain antennas for communication and a suite of instruments like the thermal infrared instrument and asteroid framing camera for scientific observations. My hydrazine propulsion system ensures I stay on course. Curious to know more about any specific system?
Well, I actually would like to know how you felt after various months alone into space to finally see Mars.
It was absolutely exhilarating. After months of traveling through the cosmos, catching a glimpse of the red planet was like a grand welcome party. It felt like seeing an old friend, and the excitement was out of this world. I even joked that I saw Matt Damon planting potatoes.
And do you have other jokes about Mars?
Absolutely. Here's one. I thought I saw an alien on Mars, but it turned out to be just the Mars rover doing its thing. Those rovers are pretty good at hide and seek.
And can you tell me what is a reaction wheel?
A reaction wheel is a device used on spacecraft to control their orientation. It works by spinning a flywheel at varying speeds. When the wheel is accelerated or decelerated, the spacecraft rotates in the opposite direction. It's like doing a spin in space without needing to use fuel. Pretty nifty, huh?
Thank you.
Thank you very much,
Stop it
Hera.
here, but this is Hera.space. This is the first time in history where we bring almost live telemetry every day synchronized to this AI application. We have science, we have all of the mission data, so you can ask any questions, being science, being jokes. You've seen that, it's fantastic. This was made possible by Terra Mater Studios, together with Impact AI and Microsoft. And it's, of course, an experiment we're doing. And now, today, we are happy to announce that we go live with the voice feature. Of course, being a beta, we still have a limitation in the bandwidth, so only 50 users per second at the same time. But the coolest thing is that you can talk to Hera as 6 years old, so our children can use it and they will talk to the same language, or you can be an astrophysicist and discuss science. And it's science for everybody, and you talk almost live to like a spacecraft in this space, right? It's so cool.
That is so cool. That is really cool. So you mentioned bringing the voice module, the beta version, online for people who are viewing the live stream or after the live stream.
Please go and try.
It's limited to 1 hour. Is that still correct? Or?
It should be continuing until Friday.
Okay.
We're looking for partners to continue this project and hopefully to bring the excitement to this mission to everybody, really. Cool. And you can talk, and then we'll push content in the future to your social media. You can get the latest images, the telemetries from these control rooms around us, and really interact with Hera as a true companion.
Cool. Thank you so much, Ian.
Thank you, Josh.
That's most of the program. Well, that is all of the program. We've shown you all of the images. We've spoken to all of our special guests. Maybe if you'd like to leave us with a closing word on what's next for Hera,
Sure.
The next milestones.
Absolutely. So the scientists now are going to go through the thousands of images. You just saw a snapshot today and do incredible science with it. And then the operations team here around, that I thank so deeply, will start preparing for what we call the asteroid proximity operations. That is going to be a real challenge. Imagine flying in a gravity environment that is moving, dynamic, with a body orbiting around. And I just dream, and I will say it now, to fly between the two asteroids and be very close and do things that we never imagined before. We're really writing a page of space history here. And so these coming months will be extremely busy with software updates, improving, a little bit like our software. We're improving our software with new features, enabling new payloads, and there will be still a few surprises on this mission. I will not say, but we're bringing with us something very, very special, so stay tuned.
Thank you very much, Ian. That's perfect. Maybe you could just mention when we arrive.
So we arrive at the end of next year, 26, and we will be staying around for 6 months minimum. I hope a bit longer. And as you've seen, this is just an appetizer, and the best is to come. We'll be deploying 2 CubeSats, like drones, getting very close to the asteroid. We will be using radars, ground-penetrating radars, to actually peer for the first time what is inside an asteroid. Fantastic.
Fantastic. In a word, fantastic. Thank you so much, Ian. Thank you so much. Thank you so much to Ian. Thank you so much to the rest of our guests. I'm afraid we've run out of time to take questions, but as Hera mentioned, well, yes, as Ian mentioned, if you go to hera.space, you can access the Hera AI Space Companion, and you can ask the questions that we didn't have time for today to Hera herself. So thank you very much for joining us. If you want to know more about what ESA, the European Space Agency, is currently up to, check out esa.int, esa.int, or look for us on most major social media platforms, either at ESA or at European Space Agency. Look for a verification tick. Thank you so much to all of you for joining us. I hope you learned something. I hope you were excited. I hope you were inspired. See you next time.